All right. Hello, everybody. My name is Decal. I go by NCO Grain for OCF. And I'm going to be your facilitator for this week. I'm sorry if you haven't seen me before. I should have been here, but alas. Okay, so this week we're going to do Networking 101, which is just, a basic introduction to how networks work and the different sort of levels of networking that we have and that you should understand as a system administrator. Okay, so as always, course resources, ed, us, etc. So first we're going to do like what makes up the network system, and then we're going to do we're going to do address and routing, which is in our network system, how do these things all communicate with each other? And after that, we're going to talk about protocols, which is after we communicate with each other, what do we do with this information? And SysAdmin tools, which is how you as a SysAdmin can interface with it. So first part of that network system,
people usually put PCAP files
which is
so this would usually have
okay. We want a network. Why do we want a network? That's because we want easy communication with different things. Okay, this is different devices, different applications, different things that want to talk to each other in some form or another. And you want that for these four primary reasons. Low latency, which is, if I send something to you, I don't want it to take 10 years, or to take a second or less. High bandwidth, I want to be able to send more than, a single pixel to you. I want to send an entire image. Ability to easily identify a computer. So that computer is not the same thing as that computer, it's not the same as that computer. It's not the same thing as your phone. And fault tolerance, which is you want things to actually get there at some reasonable speed. So conceptually, we model this as the TCP/IP stack. Here are 4 layers that we'll sort of explore more in detail. The bottom of this is the link layer. It's the closest to the hardware. That's like I have a cable, an internet, like an Ethernet cable. I plug it into my computer. That's the closest to the link layer. The application layer is things like you develop some software and you need to access something on the internet. That's all the way up to the application layer. So we'll go through each of these 4. They abstract away sort of more complex things themselves, but we'll talk about them as 4-layer one. Okay. So the link layer is very bottom of our little stack, and it is a communication between physically connected nodes. So say that computer, they each have a some network connection. That's our link layer. Okay. And these are each identified by something called a MAC address. Okay, and I'll go through what a MAC address is later. And the sort of thing you can remember for this is who can you talk to without going through a router? Okay, and this is the internet layer is the one above it. It's if you've ever seen an IP address, if you haven't, we'll go over that in a little bit. But an IP address is a part of the link layer, and it is transmitting data to different networks. So these computers are all, they can all talk to each other, but how do we get data across the world, across, different spaces, across different, just breadcrumbs? Okay. The transport layer is the one above that, and it deals primarily with reliability of your data. So some protocols like UDP will let you just send data, send it. Some like TCP will, require some reliability standards that it actually got there. And I'll explain more about both of those in a second. And the 4th layer, as I said, initially is the application layer. The application layer is your computer. How does it, in software, interact with other devices on your network, on a different network, etc. Oh yeah, some examples of this are HTTP, which is like you go to a web page, that's HTTP. FTP, if you upload stuff to our OCF servers, that's FTP, or DNS, which I'll explain momentarily. So each of these things, as you might remember here, or in different places, I talked about addresses. So in the internet layer, we have IP addresses. And in the link layer, we have MAC addresses. These are different types of addresses, and they mean different things and have different formats. So I'm going to go back here. The first is the MAC layer, the MAC address, and it looks like this up here. It is 48 bits long, and it's divided into 6 what are called octets. You can think of an octet as a byte. An octet is like the prefix oct, it's 8. Byte is 8 bits, sort of like that, where they're divided into these octets by these separators, the separators being the colons. So you see 1, 2, 3, 4, 5, 6, 6 octets. The first 3 of those octets are the identification of the manufacturer of the interface. So, you know, let's say you buy a laptop from Dell, for example. That's not going to be Dell, it'll be whoever made the interface. So that's Intel, Realtek, some other people also, I forget. It might also be Dell, I don't know. But what I'm trying to say is that it identifies the interface itself. The interface is the thing you actually like plug into and thing that does all of the routing communications, or not routing, communications. Generally, they're unique to each device, and they're used to identify devices on your local network, but not necessarily to. They're used to identify devices on your local, like that. I say unique to each device because each device is assigned a MAC address. There are different things you can do where you can emulate MAC addresses. You can choose randomized MAC addresses. So there is some. This isn't like a great rule that it's 100% always going to be unique, but the idea is that it is supposed to be unique. Now, a different type of address is an IP address. An IP address is on the internet. It is on the internet layer, and this is an address you might have seen before if you ever played Minecraft, for example. And that is an IPv4 address. The 4 means that it is divided into, well, I guess you can remember it as it's divided into 4 octets. Yeah, and so it might look something like this: 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Note that the separators are not colons, but they're instead dots. Technically, you can use other separators. I've literally never seen that though, so use at your own risk. Most programs will not let you do anything but the dot separator. IP addresses, due to how you route information between different IP addresses, they have to be unique. You have two devices on a network with the same IP address, you'll get something bad. I forget what exactly, but it's not really. It won't work in some capacity. They can be changed though. That's why traditionally you'll have your device has a MAC address. Your MAC address is always set. Your IP address changes depending on what network you plug it into. So, for example, my computer right now is plugged into, or it's wirelessly connected to Eduroam. That is different than my wireless network at home. Therefore, even though my MAC address will be the same for this interface, both here and at home, my IP address will change both here and home.
There's a
Yes, sorry.
Oh, sorry, yeah. For MAC addresses, is it per like a physical device, or is it like so like if you have a VM, will it also have a MAC address, or
I believe it's unique per network interface, so it's like every hardware interface.
okay?
I believe you can have a virtual interface with a distinct MAC address, but I'm not entirely sure. You know?
Is it possible, I suppose, to overcrowd the MAC addresses on one network if you had enough devices?
I mean, I guess so, but you would,
To the porting like centrally.
yeah, you have technically possible, realistically, um, yeah, you'd have just so many. Yeah.
Can one device have like more than one physical interfaces?
Yes. So on some computers, you might have like an Ethernet plug for wire communication and a wireless adapter. Both those would have like different MAC addresses. The idea is that they're connecting to different places potentially. You can always, of course, connect them to the same place, but the idea is that they could connect to different places. So then you'll have unique MAC addresses per interface itself. Sometimes what they will do is they'll you can like truncate or not truncate, what's it called? Aggregate interfaces together. I am not entirely sure off the top of my head what that does to the MAC addresses, but sometimes you can have two interfaces create like one interface, etc., etc. But I'm sorry, what was your original question?
What device?
Yes. Yeah, so in summary, yes, they can have more depending on how many like physical interfaces you have. Yes.
Are you always in like hexadecimal?
Typically yes. You might see it in normal decimal or like base 10 decimal, but usually you'll see it in hexadecimal, yeah. But I don't actually. I'm pretty sure they're always in hexadecimal. Anyone know? Okay. I'm gonna assume that they're always in hexadecimal. That's the answer I'll give you, but could Google too. Okay. And I'm gonna skip this portion, but this is just if you don't know about the different ways to write numbers, hexadecimal binary, you can review this slide later in the exercise after. So with an IPv4 address, going back to that, you'll often see like a slash and then a number at the end. This is not a port, as again, going back to the Minecraft example, you might have seen like a colon and then a number. That's an entirely different thing. This is called a subnet mask, and it defines the range in the address that is the network and the range in the address that defines the devices. So for example, we have /24 here, and that would mean that the first 24 bits, the first 3 octets, right, each one being 8 bits, is this to the left, 192.168.1. Okay. And then this range, 0 to 255, right, the last octet, defines all the different devices on our network. So you would only be able to have, I guess, 256 devices on your network, or on your local network, and then you'd have to have a wider network. A mask, a mask works just like an AND operation. So, if you have /24, that means that you'll have 24 ones, 8 zeros, or vice versa, depending on what you want to mask. They call it a host identifier. Yeah. Now the official names are network prefix and host identifier. Okay. But IPv4, right? You can calculate say it on this slide. Sure, yeah. IPv4, there are only 4.3 billion possible combinations of IPv4 addresses. So as such, we have something newer. It's called IPv6. And these addresses are larger, much larger. They're 128 bits instead of 32. And they're formatted again in hexadecimal. And they again have colons as separators. I should really read why they use colons as separators. I guess it's more consistent with other things. I don't know. Note though that unlike a MAC address, for instance, you don't necessarily have like this even spacing, and also you can do like shorthand in IPv6 addresses. So like if you do :0:0, you mean 0000. The shorthand rules are I don't know, I can never quite wrap my head around them, but it's best to look at a table of like what these shorthand rules mean, and they go like it enables you to write much shorter addresses despite this really long looking 128-bit. Well, what I would say about that also is that for most purposes, you can usually just write the full address and you don't have to shorten it. It's just for your sort of convenience. And sometimes programs will automatically shorten it for you. Okay. Yeah. Okay, so now I told you about these two addressing schemes, but they're sort of separate addresses, right? Like they don't really, they're not related to each other in any way. So as a result of that, we want to be able to relate them, and that is done with an ARP table, an address resolution protocol. It's an ARP table, and it translates IP addresses to addresses. I believe there is a no. There should be an example in the lab, or the lab spec where it will show you like what an ARP table is, and it will say like, okay, IP address X maps to MAC address Y. The usually the OS kernel itself will cache these values. You as a programmer generally don't have to or like worry about this. As a system administrator, you might sometimes need to look at the ARP table. You might sometimes need to clear the ARP table because it is a cache form of cache. So if you're looking at things and you're going, okay, like these devices, like not something's wrong with my devices. I changed my MAC address. I changed my IP address, whatever. You might need to clear your ARP table, modify it, or something like that. It is literally just a table. It's like not super complicated. It's just a table. Okay, and then in our IP space, I said that IP addresses are used for like wider networks, right? To connect from Berkeley to Washington D.C. And so we do this via routing. Routing is figuring out where things connect. And there's a nice tool that I will explain to you later, which will help us determine what a route from our computer to somewhere else is. You don't, in the system administrator role, you don't need to worry about how, like, actually physically sending your packets from here to here. But sometimes, you might send a packet here and it gets stuck here, and you want to know where it gets stuck. You want to know where in this process, like, things are going wrong. And so you might evaluate, like, oh, I might look and go, okay, it gets stuck there. That means that I'm going to manually maybe modify my routing table a little bit. I might, you know, send something to a different address, whatever. There are different ways to mitigate for different problems, but in general, this is something that you have a good amount, or not. You don't have a huge amount of control, like here in the middle, but you yourself can choose, like, okay, I would like to send something to X address, and then see how it's getting there, see what the problem is, contact said person, excuse me, or entity. They also routers, right? Yes.
Why do routing need to like send it like through networks to get to the computer? Why isn't it just like
Because okay, I proposed to you this problem. So, if I have a cable, yeah, and my cable is from here, my house to like here to Washington D.C., right? And then everyone else connects to this cable, or we spiderweb cables together, right? You will very quickly either run into a bandwidth problem where you can't physically send enough data through your cable, or you'll run into a latency problem of, you know, one packet being sent from your computer. If it has to go through this like spiderweb like network, it take too long. So as a result, we have routers to say, okay, I know where these things are relative to me, so I'm going to take your packet and I'm going to send it there. That's the idea, that like you maintain minimum bandwidth, or not maintain. You don't reach a saturation bandwidth, and you have low latency across a large like physical space and a large network space. So even if it's just the OCF lab, we have a lot of different devices. You don't want your devices to all, uh, you know, like that. Like if one device is downloading or not, yeah, if one device is using an entire 1 gig like Ethernet connection, like outbound Ethernet connection, then other devices can do anything. So that also gets into a deeper thing, which is like, um, there's there are ways that you can control how different computers are able to take take that outgoing bandwidth or ingoing bandwidth. But that's a deeper thing. It's fine. Okay. Next. Okay. So then when you enter something in Google, like you go search in your browser, Google, you're searching a name, right? I've just defined a bunch of IP addresses and our MAC addresses and whatnot, numbers, all numbers, right? To translate these addresses into domains, so google.com is a domain, we use something called DNS. And usually what happens is you can either set up a mapping of Google goes to X address, or what most of us do is you have somebody else cache that data for you, and you effectively send them a request. You say, I want this address. They tell you, that means that you go to this IP address. You send some data to that IP address depending on what you want to do with it. Generally, you manually setting DNS, it works and it's a good debugging tool, but it's not practical in the long term. A lot of like distributed services, if you hard code a DNS value, you might, you might not be getting the optimal like performance depending on how they've set up their distributed service. So I would not say that you should do that in a production environment. Okay, so now I've defined like all the sort of addresses and this sort of thing. But now we're going to move on to protocols. Protocols are how you actually guarantee the data that you're trying to send either gets there, or you manage that it doesn't need to get there. It just needs to try to get there. Okay. TCP is the prior, which is that it will do a sequence of going back and forth to guarantee that you actually got data. How do I phrase this? You send data with a variety of flags, and these flags denote what that information is intended to do. So for instance, here in this diagram, we have hosts A and B. Host A, let me see if I can remember which one. I don't remember which way is which, but I think host A is requesting host B to send it data. No, it wants to send data to host B. Yeah. Okay, so A wants to send data to host B. So it will send a flag to host B. Host B will reply with this ACK flag. ACK stands for acknowledge. And using it goes back and forth. It establishes some connection. It will send its data. B will acknowledge that it got the data. Then A will send some more data. B will acknowledge that it got the data. It goes on, goes on, goes on. Until A says that it's done. It gives us final, I don't know, flag, and then B will acknowledge that it received this fin flag, and then also send a fin flag that, okay, I am also done. So you see this, it goes back and forth a lot, right? This is TCP, and TCP has a lot of overhead. It takes a lot of additional packets to send all of these, confirmations. Unlike UDP, which is, I'll describe it this way. You just send packets as fast as you can. That's about it. Obviously there's some more stuff behind the scenes, but it's you basically just send data and hope it gets there. It's a lot of the times they describe it as best effort, which is no guarantee whatsoever that your data will actually be there. So examples are gaming, basically. Lossy streaming, I don't know, maybe, possibly. There's also ICMP. ICMP is the sort of protocol used for the ping tool. If you ever used it, if you haven't, you'll use it in this lab. And ICMP is not really a data transfer. You're not intending to send data. You are instead using it to transmit like messages and status info and things like this. It's primarily like a debugging, diagnostic sort of thing. And yeah, I think yes, there are different codes and statuses, and they mean different things. We will have you in this lab go through use the ping command to output some data on whether or not a site is reachable or not, and you can see that this has like different where was I going with it? You can see that like it has different return codes for the different types of errors or statuses that we actually receive or yeah, that we receive. Okay. All right, cool. And then as I said, so the how we tie all this together is you know, as sysadmin, you're not really actually implementing these things. You are using tools to and combined with your understanding of these topics to, you know, troubleshoot or set up some sort of network. So the most common of these is ping. Ping will use ICMP to effectively tell you if some host is available, if you can see it. And there are a variety of things here which it will tell you. Ping is a very good, quick first tool to sort of, you know, if you're having network issues, you can ping some addresses that you know, and that will tell you very easily what, you know, it will sort of segment your error into either is it a is it an error between my computer and my browser, let's say, or is it an error like on my ISP's side, on someone else's side? Traceroute is sort of similar vein in that it will tell you where a packet, to say Google again, where a packet is going, right? What route it takes. It literally traces the route. And it will tell you also how long that takes. This is a very sort of critical element of traceroute in that you sometimes want to know where packets are taking a long time. And so, for instance, like here, this one is taking a while compared to that one, etc., etc. Yeah, okay. There's also ARP. ARP is your way of accessing the ARP table. And as you can see here, it is formatted in this manner, which is if you're at your, these are, okay, I guess these are human readable addresses, but they can also be IP addresses. These are the hardware addresses. Hardware address means MAC address here. And this, you can ignore the rest of that. And then dig. Dig is, I forget what it stands for. It stands for something, remember, but effectively it is a way to trace or to trace like DNS. So in DNS we have a variety of different what are called records, and records come in different types. So an A record is what I described earlier. It translates a human readable name into an IPv4 address. Quad A or AAAA record translates a human readable name into an IPv6 address. There are a variety of these things, and you can read about them. But Dig will tell you, you know, okay, I would like, okay, they've not written it here, but usually what you can do is you can write dig the address you or the human readable address that you'd like here, and then the type of record that you'd like. So if you put A, you would get this. I believe A is also the default, so that's why it's displayed here. There's also IP. If you ever, you know, had issues on a Linux machine before, you might have seen what is on Linux IF config. IP is basically the same thing. It tells you about all kinds of stuff: IP addresses, routing, MAC addresses, etc. In general, I would say this combined with ping is like your first sort of step of debugging a network issue. Then you can move on to things like dig and traceroute and stuff like that. Okay. Notably, when we're looking at an IP, the response from the IP command, a lot of the times we'll be typing something like IP adder IP address, right? And you'll get these different interfaces, right? Your loopback, which is just connecting your computer to itself. And some, what do they have here? There's an Ethernet adapter and a Docker adapter. So actually, yes, to answer your earlier question, you can have virtual MAC addresses and they do change. Interesting. But notice that when we're looking at a specific interface, we'll see the IPv4 address, and if it supports IPv6, then you'll see the IPv6 address as well with those subnet masks as well at the end. /24, /64. /24 is very common for like your home network or something like that, because you don't have 257 iPads, you have one, So yeah. Okay, and okay. I think that's it. Does anybody have any questions? No questions? Okay. Well, then you can get started on the lab. I'll be here if you need any help. Just come find me, and I think your usual facilitators as well. So have fun.
Thanks.
Yeah.
Oh, no. So we're gonna discuss. Right. Wait, when is it again? Okay, good. It's before the CTA. Yeah, no, I would.